76 PSL for us, and we have planned for 2 more PSL. So the event is going to be started with the introduction of the speaker by Dr. Krea.
Thank you. So very happy. Actually, we fixed this program for last Saturday, and due to the cyclone which was hitting Chennai, we had to postpone this by a week. And of course, we did inform all the colleges, but usually most students do turn up, but so turned out that this postponing also has its effects. Anyhow, independent of that, we will start, and first of all, the program will be telecast in our own things. People actually log in from outside also, and also it will be uploaded in YouTube by the ACM itself, Anna Sentinel Library itself. We will also be putting it up in our YouTube channel which we have. So with this, we are going to start the program. Dr. K.S.Viswanathan is actually a good friend of mine, and also it will be uploaded. Is it okay?
Yeah.
So Dr. K.S.Viswanathan, I knew him much earlier, but he did his BSc and Masters from Vivekananda College here, and he did his PhD from Vanderbilt University in US. Then later, actually, he was, I've heard of him earlier, in the chemistry group of IGCAR, Indira Gandhi Center for Atomic Research in Kalpakkam. And of course, he has a lot of interest, not only in research and teaching. So I forced him to move to a place like IISER Mohali. I don't know how many of you have heard of it. It is Indian Institute for Science Education and Research. Near Chandigarh, it's Mohali. There are several such institutions where undergraduate teaching being now done all over India. Many places, Pune, Trivandrum, Tirupati, various places, about Calcutta, various places, and IISER Mohali is one of them. It's an outstanding place. Many of my friends are also there. So after serving in that, he actually was sometime in IIT as a visiting professor. Now he is also visiting professor at Krea University, which some of you might not have heard, and I'll just mention it. It's near Bhabha in the Andhra side. It's on the border of Tamil Nadu, but it's on Andhra side. In fact, I also go there to do the also visiting professor. But he is a visiting professor for several years there. And he has been handling the chemistry through experiments. And he was kind enough to accept our invitation to talk about chemistry. He has a passion for it. And to tell about experiments. We are also interested. In fact, some of us have also talked about chemistry in the kitchen, that kind of thing. So there are several things. Chemistry is kind of activity human beings always involved without being called chemistry. But now we have to go a little more systematic about how things happen, why things happen, etc. Even things like sculptures, metallic sculptures are made, uses a lot of chemistry and various activities of that kind. And now we have much more systematic, good understanding of chemistry, both from theory and experiment, like all of the science subjects. They are linked with science, so always linked to theory and experiment. And he is going to talk to us about chemistry through experiments. Okay. Now I welcome Dr. K.S.Viswanathan to take the stage. Yes. Do you have a cup?
No.
Okay.
Thank you, Professor Govindarajan, and thank you, Science Forum, for inviting me to participate in this popular science lecture series. It's a pleasure to talk to students on topics of science. What I'm going to be doing today is doing a few chemistry demonstrations. And we will see how to arrive at the mechanism or the principles behind it not so much by using reactions and formulae and so on, but by using the sort of common sense approach. And mind you, at the end of the day, chemistry is common sense approach. Chemistry is not just writing out structures and formulas and so on. It's a way of bookkeeping chemistry. So I always say the chemistry is not who came and over 15 HCl, you took HCl, 12. No, that's not chemistry really. That's only a way of bookkeeping the principles of chemistry that we have learned. The question that chemistry addresses is why do these reactions happen? What are their rates? Can I speed them up? Can I slow them down? What's their relationship to the reactivity and structure and so on? Those are the questions that chemistry really addresses. And many of them, you will see that most of them, in fact, have a very common sense approach to the whole problem. And today, when I'm going to do these experiments, together, you will see if we can find out why is the reaction going the way it does by simply using a common sense method. I will put up the equations and the structures and so on for those of you who are interested. But again, I'm emphasizing that is not the real thing. The real thing is the common sense approach. When we study chemistry at a very early age, like in schools, we are often tempted to believe that chemistry is a subject where you have to memorize. How many of you disagree with me on that? In chemistry, you have to mug up. How many of you disagree with me? How many of you agree with me? The chemistry is just, you have to memorize. You will see, in any subject, there is a certain amount of memorization that you have to resort to. If you have to call your friend by his or her name, you have to memorize it. There are certain things where you have to memorize. But that memorizing the stuff is not the essence of that subject. And that is what basically is, and we will try to understand it. So I will do 5 experiments. And I would like you all to participate with me actively in that. When I ask questions, because he said, that I will ask you questions. The question is not to find out how much you know. That's not the issue. The question is to see whether we can find out what is happening. And if you have a point of view, don't worry if it is right or wrong, just say it. And we will see how to go about it. Now I know these experiments that one does, you always need help. Right now I have my colleague from Krea University, Nagarjun, who's in charge of our lab and takes care of all the lab activities, the lab courses and so on. And he's really good at that, and he's here to help me in conducting these reactions. So big thanks to him for helping me in all this. So we will start off now. The first reaction, and mind you, most of these reactions I'm going to be talking to you, maybe you have seen it, it's all there on YouTube. I'm not doing anything that's come up completely out of the world, no. But we will see how to turn down that problem, as I said, and see whether we can analyze it through this common sense approach that I'm talking. So we will do 4 or 5 experiments depending on how much time we have. And if I cannot do all of it, I don't think that's a big deal. I'm sure they will give me time sometime later, and I can then come back and do it. The first thing I'm going to be doing is the blue bottle reaction. I'm very sure that you might have seen that. And what Nagarjun has already done is he has added the reagents in it. Basically, this is just water, and he has added some sodium hydroxide because I need a basic solution. And why we need a basic solution? That the details of the chemistry. But then he has also added glucose in this. So this is basically a basic solution of glucose. Now what he is going to do is he's going to add a small amount of a dye. So it's a blue dye. It's called methylene blue. I will show you the structure for those of you who are interested in it. But knowing the structure is not the issue now. What he will not do is the following. One, before I get started, slide. Yeah. Next one. Because this is extremely important before I start.
You have a cursor.
Oh, where is that?
Yeah, there. You are placing the table.
Sorry. So, as I said, I'm from Krea University.
Wait. Yeah, now try.
And that's the picture of the Krea University for us to see that the building out there. And that's the library, and again the academic block, and that's the chemistry laboratory that we have set up, where we have undergraduate teaching that essentially takes place. Now, before we start these reactions, I have to tell you a few things. certain safety processes that you have to practice when you do chemistry. And I'm very sure your college and school, wherever you do this, will emphasize on this. And this is extremely important. First thing, when performing an experiment, one would have to practice all required safety protocols. Protective eye goggles, coat, and shoes. As of now, I'm not having eye goggles, I'm not having a coat. Therefore, I am not right at this point in time practicing safety protocol. He's going to help me to do that. I deliberately told him I will wear it, get it just inside the point. That you have to have the buttons. Yes, first thing you have to unbutton the coat. So wearing the coat, there are two advantages to that. One, you don't really hurt yourself. Point number two, you look at it more dignified as a chemist. Doctor, this is absolutely important. You have to have safety goggles when you do these experiments because this is a spill. And find your boy, anywhere else, it's good on your hand, on your cheek, or feet. It can be treated. Any spill into your eye, you probably are going to suffer it for the rest of your life. And therefore, it's extremely important that when you work in the laboratory, you always have this eye goggle, safety goggle. If it is not supplied, buy one, just buy one. This is far less expensive than your eyes. So have this before you do any of these experiments. And just to impress upon you, both of us have done. So we are practicing safety protocol when doing these experiments. Do not perform these experiments at home. What happened? And of course, our studies are more for the full students or people who are too excited about what we see over here. Please do not do these experiments at home without proper supervision. Because some of these chemicals can be toxic, they can be corrosive, and so on. And therefore, it's extremely important that you perform these experiments only under the supervision of your teacher, if you in chemistry, like a laboratory, and so on. Chemistry experiments are a lot of fun. There's no question about it. But then they must be done with proper care. So I thought I should say this before I start doing these experiments, and that's absolutely important that you follow safety protocols. Can you give me at the end? Okay, I will not carry the mic. He has already added the dye. Solution has turned blue. There's nothing surprising about it. I added a blue dye and the solution has turned blue. And if I'm going to tell you that this is my demo, I don't think you're going to be very impressed by it. Yes. I have to, So this is my solution, and therefore that is not the impressive part. And if this is what I'm going to do and go home, I don't think you're going to be very impressed by it. But let's leave it there for a while and see if anything happens. And I hope something happens. And this is one thing that we are all magicians, for example, they're always worried that their actual come about the way they expected. So we very often keep worrying whether this will do you see anything happening?
Vishu, you may want to use the mic because it is required for this.
Oh, I think it is. Oh, okay.
The other mic is there.
Okay. See, therefore it become blue. I mean, the blue solution has turned colorless. I didn't do anything to it. I just left it there and it turned colorless. But that's interesting. That's much better than showing you a blue solution after having a blue dye. But here this will become colorless. But then we'll become blue color back again. And if I leave it for a while, you can see what's going to happen. I want you now, when this becomes whatever happens now, I will show it to you. And I want you to make some observations. Mind you, in any scientific experiment, that's what I can do with just chemistry, whether it's chemistry, whether it's biology, computer science, electronics, whatever, any experiment that you do, the first important thing is for you to make correct, unbiased observation. So we will see whether we can get this to go. I will show you the solution once something happens. Because blue it became colorless. I shook it became blue. And now waiting to see whether it happens. It's starting to get lightish color and back again. So in other words, this reaction is showing you an oscillatory behavior, but the oscillation is actually forced. After going from blue to colorless, if I just keep quiet and keep watching it, it's just going to stay colorless. But if I shake it, it becomes blue. But now I'm going to show the solution to you very carefully. Can you give me all possible observations that you can make in this? One thing is the solution has become colorless after a while. Is there any other observation that you can make?
Okay. Can I intervene one small thing? He actually, for some people who came slightly late, we usually start the program within few minutes of 4 o'clock. Okay, that's for your convenience. And I'm repeating, he added sodium hydroxide, glucose, and dye.
And then the dye, you show it automatically from blue to colorless, and when I shake it, it again becomes blue, and now it's again become color. So the colorless part is spontaneous. It becomes colorless of its own accord. But to bring it back to blue, I have to shake. I have to put an effort into it. But if I leave it again, it's going to go colorless. But before I shake it and make it blue, is there any observation that you can make in this? Is there anything?
The top layer of blue.
Yeah, the surface there is a slight blue color. So while the rest of the solution has become colorless, the top surface continues to stay blue. So these are the little observations that you must actually make. Because when you try to interpret this later on, these are the observations that will come in handy for you. And mind you, in any scientific methodology, how do you analyze a problem? You know, you do an experiment and make an observation, and after having made an observation, and as I said, the observations must be accurate and unbiased. Why am I saying this? It's a very trivial thing, you know. Actually, when you look at it, you know, why would you make a biased observation? But there are instances where people make biased observations because they think something should happen. They're already, you know, have a preconceived notion, and then they start looking at those observations that is in keeping with what they think. And this is not very uncommon. That's the reason why I'm making this point that you have to make unbiased observations. This is an unbiased observation. Solution becomes colorless when that color it becomes blue when it shakes, but the top layer continues to stay colorless. And therefore we keep all this in mind. And then how do you go about with the scientific analysis? You make an observation, and based on the observation, you come up with a hypothesis. You say, okay, if this observation has to be right, then this is what is happening. You give a scientific theory to that. You did not get a theory, it's a hypothesis. And then what do? You say, okay, if my hypothesis is right, then I must expect something else to happen. I predict. Then you go back and check whether the prediction is coming out to be right. If it comes out to be right, then your hypothesis is probably correct. I'm using the word probably because you must do this one number of times to ensure that you're really done a good science. So you make an observation, a hypothesis, you make a prediction based on the hypothesis, you go back and do experiments to check if the hypothesis is right. If it is right, then you're probably right, and then you make further hypotheses, further predictions, and so on. And then finally you come up with a law, and that's the way science grows. So we have made 2 observations. Now we don't still have enough information to come up probably with a hypothesis, but I can keep doing this experiment over and over and over and over again and see whether anything shows up. Now, president, I'm going to give credit to my granddaughter because the first time when she wanted me to do this, he normally does same this reaction in there on, but they normally do it in a glass bottle or a conical glass. But because she insisted on seeing it, I had to do it at home, and therefore I had to do it on a PET bottle. And the moment I did it in a PET bottle, a new dimension cropped up, and I will tell you what that is. Now, what we did was we took this same experiment and started this at 3 o'clock, much well before 2 people came. And this bottle, therefore, has run through maybe about 20 to 30 oscillations. So every time it became colorless, you should get made it blue, when colorless should get made it blue for 30, 25, 30 oscillations. That has only gone through 2 oscillations. So this is about 30. Now I'm just going to give it to, just feel the bottle and tell me if you see anything. Just feel, don't open it. You open an experiment. Just feel the bottle lightly. You see any distortion or anything in that bottle of the shape? Shape, okay. Just show it. Just show it something. You can say, I don't open the bottle. Feel the bottle and can read if there's anything that you observe. As opposed to this bottle. This bottle is nice and round.
Using the shape.
Yeah.
So,
Okay. Okay, for those people who have already seen this, what's your observation now? We had already a few observations. Force oscillation is one observation, and then there's a blue color at the top at the surface. And now what's the shape of the bottle?
Maybe some pressure is created inside.
Okay, the first part of your analysis is right, pressure. But is it pressure? When you say created, what do you mean? Is it an increase or decrease? Yeah.
So, like, the first observation we saw that the layer top layer was blue. So I think there must be some reaction with oxygen.
Okay.
So the interface is being blue, and when you shake it, does happen. And
Good. So he has the hypothesis, and he has the observation, and he has made a hypothesis in keeping with that observation. Now we have the other observation that the bottle has got a little distorted. When the bottle gets distorted, and it's sort of buckled in. Why would it buckle in? If it buckles in, what's happening inside? Somebody said pressure. Would you think the pressure rise or the pressure decrease? Pressure decrease. If the pressure decrease, what can be the hypothesis you can come up with? Okay, something is consumed. You got to be careful at this point that something is consumed in the air. There's a head space above the water and there is air inside. And if something is consumed there, then naturally the pressure is going to drop. What is contained in the head? This is what I'm saying. This is a very complex approach. You don't need even to know chemistry to talk about it. Now on the top here, what is the constituent of air? What's the nitrogen and oxygen? How much of nitrogen? 78 to 10. And how much of oxygen? About 20-21%. So based on this concentration, what do you think would be the one wanting to react? Based on their concentration, nitrogen is much larger in concentration than oxygen. But then we know that nitrogen is not very reactive. And again, I don't need chemistry to know that, because had nitrogen been very reactive, we would have in trouble, because when we keep breathing air and nitrogen, what if we extremely reactive? We have a problem there. So nitrogen can't be the one. And of course, we ask the chemist, he'll say, nitrogen is not reactive, it's a triple bond between the two atoms of oxygen, or a double bond. And therefore nitrogen can't be the one reacting, it has got to be the oxygen. So whether it is based on chemistry or it is based on formation approach, very quickly you will get to the point that it must be the oxygen. So when you shake it, what is happening? Oxygen is doing something and causing this to become blue. So the reaction of oxygen with the dye has become colorless when the reaction with glucose. But the colorless form of the dye reacts with oxygen and becomes colored. So why is it happening only on shaking? Because the oxygen in the water is the one that has got to react, not in the air. So when I'm shaking, what am I really doing? I am forcing the oxygen in the air to become soluble in water. There is a certain solubility of oxygen in water. But the oxygen has already been used up, in the earlier reaction. So now when I shake, what am I doing? I'm getting the oxygen in the headspace to dissolve in that water. And then that reacts with the dye and makes it again blue. But what does the glucose do? Again, makes the colors. One more shake. What are you doing? To bring the oxygen back into the water with a certain solubility. It reacts and therefore it becomes color release. And this goes on. But as you keep doing this, what happens with the oxygen? It gets consumed. the pressure drops. As the pressure drops, it buckles. If you did this reaction in a conical flask, you would not see this buckling. But because you're doing this reaction in a PET bottle, you are able to see this. And therefore, you can start using this as your common sense approach to address the problem. And therefore, all thanks to the 6-year-old who made me do this in a PET bottle. Okay. Yeah, I don't know. These little kids, when they ask me this question, some of them are really wonderful. You might not have thought of it, but they will force you to think in many, many different ways. And that's basically what it is. Okay, now we have come up with this conclusion that oxygen is the reaction, and therefore chemists would say this is a log reaction. Okay. Now, if this is true, then his argument is right. Because at the surface layer, it is already in contact with the air, and therefore the oxygen is dissolving the surface layer and keeping that surface blue, because it is already converting it to the blue form. So far my hypothesis seems to be right. Now, can you, I can't do an experiment here, but can you suggest an experiment? This is my hypothesis based on my observation. Now, based on this hypothesis, let me do one more prediction. And what could that prediction be? To show that this is absolutely right. Give me an experiment that would show that my reasoning so far is right. Yes? Heat it up. Okay, I might speed up that reaction. But I would still not. What's the other reaction? The issue between nitrogen and oxygen, right? And I've said that since nitrogen is less reactive, nitrogen was not taking part. Now, can you do the experiment that you put? Yeah. Any plan? Go ahead. Yeah, somebody listen for
already free of bucket furniture. The bottle open. You come now.
Now let's open it. See that bottom? The sound it's opening up, really undistorting that bottom. Now, if you start doing it, you can see the color is getting a little darker because I now have more oxygen in it. Earlier, it was turning out to be much lighter. Yeah, that's an extremely good point that he has made. I love my point. Anything else that you can do on the same line that he did? He said, open the bottle, let the oxygen inside, and see whether the reaction starts all over again with that much more intense. Where are I now?
It's removing the oxygen, make it that.
Oh, that's so a good point. But the problem is vacuum is that if I put it up to a vacuum pump, the water inside will just boil out. So even though that's a good thought. No, I have experimental difficulty showing that. Anything else?
So do it in another bottle.
If you show your matchstick.
Doing it in nitrogen.
Supposing I have a nitrogen cylinder, I just bubble nitrogen to it. Very, very intensively, I bubble nitrogen. What will happen? The nitrogen will go through the water. It will remove all the air on top. All the nitrogen and oxygen is gone. And now, if I shut up the bottle, what will it stop at the bottom? What will I have inside? Only nitrogen. There is no oxygen. So once the solution has become colorless, there is no more oxygen to make it color, and therefore you will find that the reaction just stops at that point. That proves for me that nitrogen is not playing a role. Therefore, it has to be the oxygen, and therefore this has to be the redox reaction. After you have come to this point, so far, mind you, it's common sense. After you have come to this point, yeah, now you have to go into the chemistry of it, seeing what does the glucose do, what does the oxygen do, and so on. These are details, and details which you must get into if you are a chemist. But the point I'm trying to make is, even if you are a non-chemist, after this point you can come and actually give a theory as to what might be happening in this whole problem. And this is the point I was trying to emphasize to begin with, that most of the chemistry problems that we look at, very often the initial phase of it would be just common sense approach. It is a nitty-gritty that you want later, the details that you want, that you may have to go into mechanisms and so on. For example, we talked about heat. That's also another thing. Because when I do the heating, what will happen? The reaction will speed up. And we know why the reaction speeds up. So I can see how the reaction can be speeded up and so on. Or I can do another experiment. I can fill it up with oxygen. If I fill it up with oxygen, what's going to happen? I'm going to get an intense color because now there's more oxygen, and therefore this whole reaction will work with that much data. So this is the glue bottle reaction, which is it's there on YouTube and so on. But what I want you to look at is the way we analyze the problem in a very simple-minded approach. Of course, once I have done that,
Wait.
It's a one.
Nice. Good.
Slow kinetics.
Good.
That's the experiment. That's the bottle, and then we put glucose, sodium hydroxide, and then we do put the cap, and we get started, and we get all of that. And the overall reaction is glucose reacts with the dye, the original form, which is blue in color. The glucose itself would get oxidized, and the dye would get reduced, which is colorless. And then when you have oxygen, that reduced form of the dye, remember the structures. You're not interested in these structures, you're not interested in the reaction, doesn't matter. But if you're a chemist, you want to get interested in these reactions. Therefore, this is for everybody. But the point is that you can actually use very common sense approach to all the problem. Okay, any questions on this or any discussion or anything else that you want to add to what we just said? Yeah.
And also incorporate kinetics into this.
Absolutely. You can incorporate kinetics into this, you can incorporate interference with something else, and so on. And therefore, in any chemistry reaction that the reaction itself might be simple, but if you start looking at the details of the whole process, it can lead to an entire set of complexity. And sometimes it can keep you busy for a few years doing research on the reaction. Yes, the kinetics of the reaction is extremely important. Do it in water, do it in a different solvent, and see what happens.
Here itself you will add some more water.
Yeah.
And monitor the time taken for color.
That's correct. Basically, where is the concentration of glucose, where is the concentration of sodium hydroxide, and so on, and where is the concentration of the dye itself. Because lesser the dye, it's going to take slower for the whole process. So the kinetics can be done simply by varying the concentration of glucose. See whether sodium hydroxide has an effect, see whether the dye has an effect. That's all the kinetics is actually done. Okay.
Can we change the time?
Yes, you can change the dye. The only thing is, the dye must have a redox potential such that it can react with the oxygen at room temperature and change its color. If that is not facile, then it's not going to have field. Dyes usually have a redox chemistry that goes from one color to the other. But how easy is that redox going to be? If that redox reaction is easy, like in this case, then you will see a visual effect. If you don't have that visual effect, then the demo doesn't really work well. And therefore that much. But in principle, your question is right. Can I think of another dye? Yes. Provided the change in color of the dye can be affected by oxygen under ambient conditions.
Salty water.
Pardon?
Salty water.
Salty water. Yeah. So if you have salty water, in this case, it does not affect you so much. I'm just giving you the answer, but there will be another reaction that I will show you. And I will also give you a little history or some story anecdote where salty water actually has a very serious effect on the whole process. Okay. The next one is another very simple reaction, which again you might, many of you have seen, but I'm going to do it and we will see another concept in chemistry that can be thought of when you do this. And that's the whole process of the different food phase that we do. And what Nagarjun is going to do, we're going to do the reaction. But we didn't want to spoil the table and chairs for the library, so we have or we will. And what we have inside is hydrogen peroxide and some detergent. Okay, this one he's adding the detergent now. And hydrogen peroxide, is it a stable compound or what will happen to hydrogen peroxide if you buy and leave it around? It'll decompose. It's not a very stable compound, but it's stable enough that you can keep it in the water. And that's the reason why we have it. It's adding detergent for the time. And you see nothing is happening now. So this one moment you're the one that you're taking. Just add, don't add it inside, just put it on the side. The dye is only for visual effect. The dye has nothing to do with the experiment. So what he has basically done is put a hydrogen peroxide in the flask and measuring cylinder, and he has added some detergent. And what will detergents do when you agitate them? You will get foam. So you know why he's added. He wants foam. So he added the detergent to get some foam. And so far, nothing is there to see. Is there the solution and the peroxide and the detergent? And now he's going to add something. In other words, the decomposition of peroxide. Now just imagine, If the peroxide was decomposing and liberating oxygen and the oxygen wants to come out, what will it do? It will churn the solution. And if it churns the solution, what will happen to that solution? It should form. But there is no forming. There is no forming. So which means the peroxide is not really decomposed. So now what he's going to do, he's going to add a little solution. I'll tell you what the solution is a little later. Just add it. Finally, there's a foam. So what does this mean? Oh, look at that. Don't come out, don't come out. If you're old enough to be chemistry, so what has happened here? Nothing happened for quite some time. With the peroxide and the oxygen, nothing happened. But the moment he added a solution, and the solution was very benign potassium iodide. That's it. It was potassium iodide. And it got nothing to do with anything, in the word reaction. What potassium iodide did was it acted as a catalyst for the decomposition of peroxide. So he asked a question about kinetics, he asked a question about kinetics. Very often, why do we study kinetics? We study kinetics because we want to know the rates of the reaction. And if the rate is slow, and the industry wants the rate to go, industries always want the rates to go fast. There is no point in making a medicine which you can make at the rate of 1 kilogram per year. That's not feasible at all. We want to make it quickly enough to make profits. So they always will ask you to, is there a way to speed up my reaction? So therefore you study kinetics, and if you have to speed up your reaction, we know what to do. We have to think about catalyst. And the industrial processes in mind, you use catalysts to speed up the reaction so that they make it industrially viable. That is the situation over here. Peroxide was not willing to decompose under normal conditions, even though it's not very stable, it decomposes at a very slow rate. But the slow rate is visually very unattractive. So what did we do? We just added a small amount of potassium iodide. And once you added potassium iodide, the decomposition just took off in a big hurry. And then what happened was that the oxygen came out in lots of quantity. It churned up that solution, and when it churned up that solution, you had foam. And therefore you saw that. So in other words, what we are really demonstrating here is the whole process of chemical kinetics being speeded up by a catalyst. And we know how a catalyst works and why a catalyst works the way we do and so forth. So if anytime you want to introduce the concept of catalyst as a teacher, this is the best reaction. Do it first, talk to them about catalyst, but they know what a catalyst does because they have seen it, and then you start telling them what catalyst is, they will listen to you. But if you start off on day one with the catalyst is coming and speeds up the reaction, affects the potential surface and blah blah, nobody's going to listen to you. First show a demo, tell them how the catalyst works, and then talk to them about the chemical principles behind how the catalyst actually works. Any question or any other suggestion or any things that you have? Yes.
You can do the transmission.
Yeah, because what you can actually do is, you could have a test for oxygen, by putting a little splinter and so on. But yeah, but then what Nagarjuna and I did was we decided that we are not going to have any experiment with flame, or in fact, there was one chemical volcano experiment, but we decided not to do it. Because in a chemistry laboratory, you can do all these things, but in a thing over here, which is a library, we didn't want to set the library on fire and go away. Therefore, we decided that we will not do any explosion experiment. We will not do. There are many interesting explosion experiments. But if you come to Krea, we will show you to the lab.
So we have fire alarm system. So that start spraying water.
Yeah, and that's it. All will be wet by now. So therefore, we decided that we would not. Otherwise, what he's saying is right. If you have to show that oxygen is there, just have a candle, a split, light a splitter. It will catch fire and the flame will go on. And you will know oxygen is there, and there will be things that you can do. But many of these flame experiments and explosion experiments, we said we will not do. But we chose those experiments which are, harmless and which are quiet in terms of any explosions and no fire that is basically lost. Okay. Now we will do the next experiment. Which one are you getting? Okay. Let me do that. I'm doing that. The next one I'm going to do, and I've been trying to learn jugglery for a while. So I want to see whether I can try that with you, and if it works, that would be good for me. So I've got three empty classes. I've got these. Yeah, I'm going to pour water into one of these glasses, and I'm going to keep shocking them. I'm going to ask you to figure out the one in which water is. And I believe that I'm quite good at it, like you will not be in a position to figure out which one it is. I believe that. Okay, here's the water. I put water in this. You have seen that. Okay, now I'm going to juggle this, and I'm going to ask you to figure out eventually in which part the water is. Let me try it one more. Okay, let me get tried one more. I think it's not working. I'll tell you, just give me one more chance. Because I practiced it so well, and I thought I would, I'm good at it. But I can't reason. This isn't working. So I'm going to I put the water into this cup, and I'm going to challenge you this time that you will not get it. And my challenge is the following: that once you pick a cup, I'm going to take that cup and pour it over my head. Because if you are right, I'm wet. But if you are wrong, say I know that I'm wet. Yeah. Okay, now let's start. Ready? So I'll stand by my promise. Problem this time.
Are there any close countries?
Yeah, I mean, if I got this, but let me answer your first question.
What I mean is that on the document which evaporate the water. So you delay, you want to evaporate it, so you delay when you are conversated.
He's got most of the time. See, I'm not a juggler. I was pretending to be a juggler. I'm not. I can't even move the cup properly, and you could see, I mean, because this is the thing they play with cards, right? And if I were to do that, I would be losing everything. So I'm terrible. But I still challenge you because I knew that in the third attempt, I'm going to play a trick on you. So the first time when I put the water into an empty cup, in the third time when I did it, that cup already had chemicals inside, I think correctly predicted. And that chemical did not evaporate the water, so that's where you were the But the idea is, that cup actually contained sodium polyacrylate. Now, sodium polyacrylate is a compound that absorbs water. Tremendous. In other words, 1 gram of sodium acrylate can absorb 100 grams of water. And he's extremely observant. He's also tried when he said, "You are making unnecessary conversation with us." Very sharp. You are making unnecessary conversation. I was making unnecessary conversation. I wanted to make sure that water got put up. Because if I did it too quickly, I would be wet. So I have to A few seconds, not terribly, just a few seconds, but I just want to make sure that I don't go home wet. And that's the reason why I played a little, I was just basically talking gibberish. I was not even telling you anything useful. I was just talking.
Silica gel, what they call it.
That was polyacrylate.
Okay.
Silica gel can do it, but polyacrylate is extremely absorbent. And 1 gram of polyacrylate can absorb roughly around 100 to 300 grams of water. And what does that polyacrylate do? And now mind you, okay, now that I have said this, if you are an entrepreneur, where would you use the polyacrylate? Diaper industry. People have already done that because in the diaper industry, you want to absorb the water immediately. And therefore, the diaper industry actually uses polyacrylate. And this is what I did. And I know for a moment I got you. I know you were all still happy. Go back to it. But I didn't. Okay. That's the structure polyacrylate. It doesn't matter that what the structure is. It's got a negative part of the molecule and a positive sodium. So what the water does is it takes the sodium and gets trapped in it. And then we have all chemists and physicists and biologists who studied hydrogen bonds and so on. The water gets trapped inside all of that. And therefore the water is totally immovable. I have trapped it. And if you actually look at it inside, you know laptop for 90 minutes. Like a gel. It basically forms a gel, and that's how the whole thing happens. So therefore, that was the reaction in which I essentially trapped water. And I've just showed you the polyacrylate putting the water inside and I showed you that it formed a gel. I just thought I would use maybe the mid energy gain and put myself in a very difficult situation to do that. But the point of the chemistry there was that here's a molecule that can trap water 100 times its capacity. And therefore, that could be used it is used in the diaper industry and many other industries where you have to hold back water and you need a form gel.
Can I ask you a small question?
Yeah.
In people sell or a drink called Madura Jigirgata, where they use badam pisi, it's actually gum from the badam tree. And they pour water and keep it for some time. And after some time, it becomes gel, like what you showed. Exactly like yes. Yeah. Is it also
The chemistry would be very similar. Because again, I would have a network of molecules. And then water would get trapped in between and they would respond. See, any gel, that's what it does. As a dry powder, it has got places where it can store water and trap water by either ionic interactions or by hydrogen bonding interactions. Once it does that, and depending on how well you have structured that powder, you can trap an enormous amount of water. And this is what it is. So this is polyacrylate is extremely good at that. But the one
so actually you can buy this badam resin and dry. Then within 1 hour it becomes gel.
and that's the thing. Sometimes what happens is kinetics again when we compare kinetics will be slow. So the water has to diffuse inside, it may not be so easy. So the kinetics may be slow. In polyacrylate, the kinetics is very fast. I didn't trust it, that's why I did that do stop for some time, just to make sure that it got gelled up. But the point is, okay, how much more time do I have?
You can go for one more experiment.
Okay, I'll just do one more experiment. We will do the on screen.
Because some of the audience came late.
Yes. Okay. Now we're going to do see the very first reaction. We saw oscillation, the blue water, where we had the reaction going from blue to colorless, and then from colorless back to blue. But that part of the reverse reaction, we had to force it. It was not a spontaneous oscillation, it was a forced oscillation. It's almost like a pendulum wanting to go to one end and then it stops. And you have to push it and then it comes back and again comes and stops. So every time you have to keep the pendulum in oscillation, you have to keep it putting every now and then. But pendulum doesn't work that way. The pendulum actually has spontaneous oscillation. And what we're going to do now is to show you a reaction which actually has spontaneous oscillation. And you will see. And when I show that reaction, I will address the question that you asked earlier about sodium salt. And so what he has done is he's already mixed a few solutions. He won't worry about what he has mixed. Let's first get this reaction. Then we will try to address it through common sense approach. And then we will come to the nitty-gritty of the chemistry. So
So can we come a little bit back? Yeah, catching.
is that? Yeah. Okay, I didn't know it. So in fact, just to prove to you that I'm not doing anything, I leave it on the table. And see what happens now. Can you all say the last thing?
Yeah, because I can show you. I'll show you.
Oscillating.
Color is oscillating. It is brown and dark.
It goes from blue color to
Oh,
an
yes.
amber color. And then
Comes back.
stays there. And I'm not changing it this time, mind you. Then
Comes back.
so this is the spontaneous oscillation. No forcing. This is just like a pendulum. You pluck it and you leave it and it will go on. Will the pendulum go on forever?
No.
What happens?
Which level?
Yeah, there are damping, we call it damping, right? There are friction that types and air in that go on. That will cause damping and it will eventually stop. The very same principle will happen here also. Don't expect this to go on for the next 20 years. In a few minutes from now, or in a half an hour from now, you will see that the color change will happen less and less frequently. And eventually it will stick onto some color, depending on the concentration of the reagent. But to begin with, mind you, it is oscillating. So now the question is, the first reaction was oscillating, but I had to force it to oscillate. In this reaction, I'm not forcing it, it's doing a spontaneous oscillation. So why would something spontaneously oscillate? Why would the reaction go from state A, which is amber, to state B, which is blue, back to state A, which is amber, state B to blue, and so on and so forth? So the question is, what is this oscillation?
No, let's do this.
It is not exactly a reversible reaction, mind you. A plus B goes to P plus B, and then P plus B goes back to A. That's a reversible reaction. Yeah, you are.
Just observe that, first நீங்க பண்ணும்போது வந்து molecules ஓட motion வந்து உள்ளுக்குள்ள ரேண்டமா நடக்கும். நீங்க போஸ்ட் பண்ணி அந்த moleculeோட motion எடுத்துட்டீங்க. பட் இது ஆம்பர் கலர்ல மாறும்போது அந்த கிளியரா தெரியுது molecules ஓட motion தொடர்ந்து நடந்துட்டே இருக்கு. So oscillates still அந்த molecules ஓட motion
Okay. He's made bunch of good observations for molecular motion, but molecular motion, mind you, at room temperature, molecules will move whether. What we really see are bubbles and particles and so on. We can't see molecular motion, but we can infer molecular motion. And at any temperature, like room temperature, or even if you go to lower temperatures like 10, 5, minus, and so on, the molecules are in motion. And of course, quantum mechanics will come and tell you, even if you go to 0, they're not quiet. The world is never quiet. There's something happening even when you go to absolute zero. So molecular motion is there. But is that the reason for the thing? In every reaction, molecular motion is there. But why am I seeing oscillation only in this reaction? So something very funny is happening in the reaction. So what I will do, I will just show you a little, let's look at a reaction scheme. If we had much, lots of time, we will try to discuss this slowly, but since we are running short of time, what I will do for you now is give you a reaction scheme and I will tell you what might be happening. Let us say I have a reaction scheme. You don't need chemistry for it. A plus B going to C plus B. That's the reaction. And then C reacts with E and becomes F. So this is the reaction. But now just imagine a situation in which C, we talked about catalysis, right? And what does catalysis do? Can you think of negative catalysis? Yeah. So in this case, what can happen? Supposing, let us say, C is the negative catalyst for that first reaction. So what does that, what would that do? A plus B gives me C plus D, but C is the negative catalyst for that reaction itself. So what would happen after a while? The reaction starts off in a jiffy, but then it slows down. So I produce C to begin with, huge burst, and then no more C is produced because the reaction has become so slow, or it is in fact stopped, because C is inhibiting its own production. But what is the next reaction doing?
C is consumed.
C is consumed. So the next reaction, let's say, has a rate which is reasonably good, and it consumes C. What will happen to C now? C will drop. Once C drops, what should happen to the first reaction? It will start again. It will again start and come to a point where C is in large excess, but then it will stop because the reaction has been negatively catalyzed. But then the next reaction consumes C, and therefore the C concentration will drop again. Again, the first reaction will pick up. So now I have given C a blue colored stuff. So every time the C is formed, let us say the blue color is there, and then the reaction becomes so slow. So no more C is produced. And then C is consumed by the second reaction, and therefore it becomes colorless. And now there is no C to begin with, and therefore the first reaction will start all over again, and therefore this will go on. This is what we call as the negative feedback. So the C is inhibiting its own reaction. And mind you, in biology, I'm very sure there are biology students over here, since it's seen very often. What does the body actually do? Sometimes it produces certain enzyme, it produces certain hormones or whatever, but it does not keep producing it forever. At some point, the body knows that this is too much. So the very concentration of that enzyme would actually inhibit the production of that enzyme. So negative catalysis or a negative feedback is a very common affair in biology. It's a very common affair in many chemistry. It's a common affair in physics, electronics, lasers, and what have you. So this negative feedback is something that's very, very common. And it is a negative feedback that will cause oscillations to occur. And what's the basis of the whole process? Something that is produced is inhibiting its own production. If that were to be the case, and then there is another reaction, if I didn't have the second reaction, the whole thing would have just stopped. But the second reaction is consuming C to trigger the first reaction all over again. And finally, the kinetics of the second reaction has to be such that these things happen in real time scales. The second reaction was very, very slow. What would happen? You would produce blue, but to get the number, you have to come back tomorrow. But that doesn't happen because the second reaction is quick enough that it consumes the ID, and therefore the first reaction starts all over again in quick time, and you see this oscillation. And that was not happening in the first reaction. The first reaction had to force the oscillation. Over here, the oscillation has been set up because of this negative feedback that there is. In other words, while we looked at catalysis as the process in the hydrogen peroxide decomposition, here we are looking at the process of negative catalysis, which is actually causing the oscillations to occur. And negative catalysis, like I said, is a very common affair in biology. There are many situations where otherwise the body would simply keep producing an hormone forever. That is bad. It knows when to stop, and it is a negative catalysis or a negative feedback that causes the concentrations to stay where they should be. And once that is consumed and the concentration drops, it will again produce more of it. For example, insulin. You don't keep, body doesn't keep producing insulin forever. It produces it on demand. And therefore, very, very similar thing happens in many, many biological processes. And this reaction, mind you, is not simple at all. This was done by two teachers, Biggs and Rosher, to demonstrate chemical oscillation. But then that's all the reaction scheme. Go to any Google search and you will get all the details of the reaction. I don't want to spoil the whole fun of this thought process by giving you the nitty-gritty. But this nitty-gritty is important for you to understand in great detail. This experiment is not a simple experiment. When I say that C is preventing its own production, it's a very complex process by which it stops that production. In this case, there are two different types of mechanisms, ionic and radical take over, sometimes blah, 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 and goes on. But the point is the production of C inhibits its own production. And that's the reason why you have the process.
It's like coupled oscillations.
Yeah, coupled oscillations in mechanical system, there is very, very there is a couple of the energy keeps going from one to the other. Here, what is happening is I'm draining away one, but the net effect is the same. Like when I have two that are coupled, then I just plug one and leave it. That will oscillate for a while and then that will stop
Travel.
because the oscillation is built by a later and it will go back and forth. Absolutely true. But there is an energy exchange between these two. Here I'm not really talking so much about energy exchange. The net effect is the same. The net result is the same. But the mechanism that is happening between the coupled oscillator and this reaction is different. In this case, it's a negative feedback. In that case, it's an energy exchange between the two. And that's what I think I have come to the end of my time.
It's almost
Okay.
5:15.
People ready for one more?
Have a question on the special.
Are you ready for one more? Okay. One more.
Yeah, we reach back at 5:30. Question answer.
Oh, okay. But you will prepare that. You will just prepare one more experiment. But the question that you asked earlier, the salt, will it affect that reaction? In this case, it affects it in a huge way. Because it's I minus that is taking part in the reaction. If I have Cl minus, then that will really mess up with the whole reaction. And the oscillation actually does not even occur if I take water that has got contamination with chloride. And I learned it the hard way. What happened was, I was an IGCAR at that time, and IIT Madras had asked me to come and do some demo for school children. So I had done this experiment for many times. So I took some of these chemicals. I said, distilled water, I don't have to take it to IIT. IIT Madras will have distilled water. So I will take it from them. I don't have to carry. In fact, we carried 2 liters of distilled water here. Because I can't expect another technical library to give me distilled water. But IIT, I thought, this sort of problem. So I got everything done. I called the person who was helping me. I said, give him a bottle. I said, can you please get me distilled water in this? So he went out and came back a little later and handed me the bottle. I started a reaction. And as I told you, one of the biggest fears that I have is you start something and it doesn't work, and I keep looking at it. And I kept looking at it, the oscillation wasn't occurring. High school kids and when high school kids can be extremely so what are you expecting to see? What are you expecting to show us? I said, I can't tell you that because if I eventually get it to work, the fun is lost. Therefore, I can't tell you, but I still don't know why it is not working. And I kept staring and staring at it. And I didn't know why a reaction which I have done so many times and it had worked every single time now did not work. Then I called that person. I said, did you get me distilled water? And he said, no, sir, the lab is too far away. So I just went to the tap here and I said, no, sir, I need distilled water. Can you please go get distilled water? Go to the lab and get it. So he went to the lab and got distilled water, came back after about 20 minutes, got the distilled water. We did this reaction, it worked. That day I realized that the chloride can actually interfere. I learned that. Then I went back and checked the literature on it. And sure enough, people have studied this. And chloride will interfere with the iodide. So this is potassium iodide solution. And therefore, chloride, bromide, will interfere completely from every organism. So that can happen. But there are reactions where these things can happen. And we thought the light. Yes. Yes. Okay, we have to turn the lights off. So, yeah, all lights off. And can you put the screen? Don't be afraid. Is there a way to turn that light off? Turn it.
Yeah.
Okay. I don't know how effective this will be. This is a real dark room for you to see it. So we have put some solutions and let's see what happens over here. And again, he's going to add some peroxide. Most of the reaction that we have is based on peroxide. Yeah, it came out much better than I expected. Normally, when you turn the light forward, it's really dark. It shows up really well. Okay, and this is the reaction that is what we call. Yeah, now we can have the light on. And this is the last experiment. I will stop after this. This is what we call as luminol. It's a compound. You've got nitrogen ring, carbon ring, aromatic ring, and so on. Forget all that. What the reaction does is it takes that molecule And in the presence of iron as a catalyst, I think we use copper as a catalyst. Right? Yeah, you can use copper as a catalyst or iron as a catalyst. And there's a reason why I'm mentioning iron. You use iron as a catalyst, then the reaction will occur. You get that brilliant blue color. And why does that happen? You take the luminol, the presence of iron and peroxide, it undergoes a chemical reaction and produces a molecule, a product, which is in an excited state. You know, any molecule in an excited state will drop to the ground state and give you light, right? So if I take wires, for example, a wire and I heat it, it glows. Why? Because when I heat it, I'm taking the molecule from the ground state and exciting it, and then when they return to the ground state, they emit light. So the same way over here, you know, the molecule has been produced, the chemical reaction has produced the molecule in an excited state, and then the molecule returns to the ground state, giving me that light, and we call that as chemiluminescence. When biological species do it, we call it as bioluminescence, and you will see fireflies. So they are actually doing reactions in which they produce molecules in the excited state, and when they return to the ground state, you have the color that is emitted. And that's basically what it is. Now the trick here, or the important thing here, is that the iron is the catalyst. So I showed you a little trick. I pretended to be a jugglery expert, you know, and I did that and I failed. Now, if I were to, you know, commit a murder, which I have not done, which I won't see blood, you know, you slash somebody and there's blood. What's the first thing the culprit would do? Clean up that place and then leave. So you clean up that place and then leave, but the police then figure out that the murder must have been committed here, but there is no sign of blood there because it's all being cleaned up. What they would basically do, of course, today they use other methods, but this was in early times. You actually can spray this luminol and peroxide. If blood has been present there for some time, you would have left behind some iron. Now, iron as a catalyst will start to produce these molecules in the excited state and they will glow. So, the moment you shine some UV light, you can actually see the glow. And many murder cases have been solved essentially by spraying luminol, peroxide, and looking at it in UV light. And you will actually see the exact design of the blood stain. Even though the floor looks absolutely clean, the murderer cannot remove every trace of iron. He's going to leave behind something. And therefore, the luminol experiment is actually an extremely good forensic tool to detect the presence of blood. And therefore, it has been used by forensic experts to actually do that. So, what I showed you was a classic case of chemiluminescence. It's academically very interesting because you're producing molecules in excited state and you can look at the emission and so on and so forth. But it has useful applications in the forensic chemistry because it's a good test for the presence of blood. And there are people who, of course, I won't do that because certain reasons, but there are people who will do the very same reaction, you know, they want to make it very dramatic, they will poke the thing against some show this and then show the blue color. For various reasons, I won't do that, but that's the one way by which you can make the whole demonstration extremely effective. And that's a luminol reaction. I think we'll stop here, let's not get converted to reaction. That's because if we can come back later, there are other things that we can do. So we did that clear and we will show you many more reactions for you at that point in time. Thanks a lot. Any questions?
Before getting the question and suggestion, let me ask the participant another feedback form. So you can share the link for providing your feedback. Please click the link and fill up the feedback form. This will help us to I will also encourage you to give your email ID and mobile contact details so that we will contact you for our future programs.
One question is there.
Yes, I have a question.
Can we use
chemistry?
Yeah, we have one question. Can you use Castle-Mayer test to check the blood strains?
Can you find it?
Castle-Mayer test.
I don't know because I don't know the Castle-Mayer test. As simple as that.
That's good.
I've heard of it, but I don't remember it.
Yeah. Anyone have any questions?
Yes, can this sodium polyacrylate be replaced with any natural product? Like sir said, one of the examples of balance, right?
Yeah.
We can add some other catalyst to absorb so that it can absorb easily or fastly.
I'm sure there are natural product that we do the job, because nature, mind you, is extremely sensitive to the fact that water has to be absorbed, water has to be retained and so on. So nature does that. So I'm very sure that, all these techniques and other materials, it's very sure we can absorb moisture and so on. But if you actually go back and look at the way it does, we always start by finding the required material in nature. Like, for example, you look at clean, the treatment for malaria. But then, depending on nature, so very often you will find if I start making it in because that will make much more about nature. The truth is always, you will get the idea of nature, but very often you will go back to the industry.
send it through post.
So to answer your question, yes, I'm very sure there are natural products which will absorb the water to a large extent. But can it depend on it from a single metal? No, I'm not really sure.
The point whether we can
Solely polyethylene.
it or discontinue அப்படிங்கிற பொசிஷனுக்கு நான் இருக்கிறேன்.
Depends upon the application.
நீங்க என்ன வேணும்?
What's the amount of water you want to apply?
Depend on nature that you need.
You cannot continue this move.
Yeah.
Yes. The same thing that because something like robot, daily that they are also on the same kind of things. But it's the same thing, but it's the same chemical.
I think in the pilot plant, you're very good. But what is the key point of the day? I don't know how many of you that I think I saw the effect extremely wonderfully in the sea. And that was the first time I tried to sometime in 1990. So I was actually living on on a house which was on the beach. So you open my door and 200 meters out would be the sea. And one particular night we saw the waves were actually greenish blue. And we didn't know what the hell it was at that point in time. And of course, immediately there was all this talk going about all the reactor people that let out radium into the water and of course I used to argue that if you let out radium into the water, it should be glowing all the time. It should not be glowing only on the crest of the wave. And of course, what I did, I think some people remember that we collected this water in a bottle, brought it back home, and turned out all the lights. Okay. Now light to be emitted. And then shake it again, so it was basically agitation that was causing the light emission. And that is also in terms, there's a terminology called triboluminescence, where you convert mechanical energy or heat to light. And then went back to read about this. Then I figured out I forget the name of that organism now. What it essentially does is, when it is agitated in the water, it sends out the light more than a defense mechanism. So when there are other fishes that come to eat it, and there's agitation in the water, this puts out this light, you scare the other fish away, and then you basically using it as a defense mechanism. It's again the same thing when hinting causes the molecules to go into an excited state, and then it drops down to providing light, and that is basically the effect. It's again chemiluminescent, but it's got a more specific name called triboluminescence, tribos's friction to understand. I've heard this, but I've not ever tried it. This candy, Kalpakkam. So if you break Kalpakkam, you can get a light emission. But that is again triboluminescence, where you are converting mechanical energy to light. We know in spectroscopy, I can convert light to heat, and that is the non-radiated heat. This is the reverse of that I convert heat to light.
So any substitute for luminar, because luminar is slightly costly.
I know. I think there are some molecules because if you go into the literature of all these demos, there are some compounds, but apparently luminar is the one that gives you the best effect, and therefore I think there are. I don't remember the name, but there are.
So in between you said, come to Krea lab, we'll show you this and show you that. So what does that mean? I mean, come.
There are many other experiments.
No, I know that.
He wants
No, I'm just inviting you to our. Okay, is there any way that I can come there?
No big deal. All you have to do is you just let us know when you want to come.
Okay.
For that, we can arrange for you to go around and see. Okay. And I think you have my email ID. So we can get in touch with us. Yeah, but I'm just making more as a, I'm doing a nice, yes.
We'll make arrangement.
Yeah, I'm just trying to be a nice coach and visit us and I can tell you. It's a very new university, though, 4 years old. It's a liberal arts and science.
And we have industrial visit like,
Fun.
and we have industrial visit, a similar thing to Krea lab.
Yeah, I mean, you can come to Krea lab and force, you can force it as an induction because that is between you and your finding it. But that's obviously okay. We will certainly entertain you. And yes.
So you want radium as jewelry worn by women? As radium as jewelry.
Radium as jewelry. No, radium as see all radium is radioactive. Therefore, you wouldn't want to use it as jewelry in any case.
She will be a married jewelry.
Pardon?
She will be a married jewelry.
So they used to be in old watches where they would say radium tint and all that. I don't know how much of it. Yeah. So, but radium by itself is radioactive, and therefore you wouldn't ever want to use it as a radioactive, as a jewelry material at all. That is to be, it can't be protected by all. Yeah. Yeah.
It can to the married jewelry type of that can.
Yeah. Because Madam Curie was of course, she was exposed to a whole host of other things. She was the pitch blend that she was using. And that was she was exposed to a whole host of radioactive material. Radiation safety was not an issue at that time because we didn't even know about radioactivity at that time. Now we are, and therefore it would be not worth the while having illegal. Yeah. Yeah. Sure.
It's giving a recommend for a order to carry all the evidence. From your experience, which can with your experience, would you recommend?
He's asking a question that is fine. I want to get rid of all the evidence and so on.
No, it was apparently used in England by some kind of a Russian spy on the polonium, this thing which is handed to them, and takes effect much later.
The Russian component leader was.
Some organizations are there, but probably chemistry can explain it much better.
Yeah.
Arsenic poison, what is arsenic poison?
Arsenic poisoning can be figured out nowadays by easily. Because we have analytical. See, arsenic in water, the WHO regulation is 5 parts per billion, 5 nanograms per ml, and 5 nanograms per liter. And therefore, that is not a.
Yeah.
That is very easily, you can measure it. By,
generated
you want to give there are analytical tools which can very easily figure that out. There was a movie once that I think that movie was Homi, and where they said if you do carbon monoxide poisoning, it is very hard to figure out. Come on. Operation theater. Yeah. But that's totally. And because the answer to your question would not be possible because chemistry has gone to such a point where you can estimate even nothing. If I have nothing, I can estimate. So we have got I'm just trying to exaggerate my point. But what I'm trying to make is extremely small concentration. We have the analytical tools to figure it out. And therefore, the question that you raised, it would be very hard for anybody to do that because chemistry will find you out.
Chemistry can ask for
We already put a photo on.
We have one question from the remote participant.
Using a loophole to erase the website number.
No,
Also extremely can counter this person.
yeah.
You can a loophole to erase it.
Well, you can't see, at the end of the day, whatever you do to erase it. Earlier, if you, let's say, a few watches, you might leave behind 5 ppm. And let us say in those days, 5 ppm could not be found out. Therefore, that guy would get it. Today, you can find out 5 ppm. You can find out 5 ppt, you can find out 5 ppt even today. So it means, after committing whatever acts that were committed, you would have to spend the rest of the time cleaning the scraper. And that basically what it is. Because any cleaning process is asymptotic, you clean it little less, clean it then a little less, but you're not going to ever get rid of it completely. That's the thing.
Now we have one question from the remote participant.
Uh-huh.
Good evening, sir. To convert the concentrated H2SO4 into a diluted state, water will mix it. What kind of chemical reaction takes place in that process?
That is basically, it's a dilution process. That's what we call the heat of dilution. And that heat of dilution is extremely large, and that's the reason why when you add sulfuric acid to water, you're doing many things. You're breaking the bond between water, so hydrogen bond and stuff. You're breaking the bond between sulfuric acid and so on, and therefore you're causing solvation of these molecules. And in that process, you have to break the bond, and the net effect is you're putting out heat. And that's a lot of heat of dilution in that case is quite large. And that's the reason why they always say you have to add sulfuric acid to water and not water to sulfuric acid. That is very significant. And this is because of the fact that the dilution process that you are causing, and it involves a lot of, and that heat is enormous.
There is one more explanation about this. In a book, experiments without reaction. They talk about the density of a sulfuric acid.
PSL.
Yeah.
PSL.
Basically inside the water. This heavy wet
Okay.
absorbed by water. But if you do it the other way, it forms a layer on top of it, it splatters out, giving all this content.
That's correct. That's the books. I was working in an industry, and where we had to do the dilution, and the people who are running this machine, they would have to go. But the explanation that I would have to give them in the way that they would understand was the following: that if you add water and you put sulfuric acid, and even if it splatters, what splatters is dilute sulfuric acid only. But if you do it the other way around and if it splatters, what splatters is coordinated sulfuric acid. Therefore, don't go there. I know this way they would remember it. And after that, entity and issues and so on. But the thing was that in sulfuric acid being added to water, any splash would be dilute sulfuric acid on you. Perfectly far better than the other way. But what you're saying is also an issue, is an issue, but an important issue. Was it just go in and then don't time you want to come.
So we are closing down now. We have been asked to really by 6 o'clock. So we are 3 minutes more. Yeah, couple of things. One is now, some of you may want the certificate. Now we have automated the certificate process. Provided if you are filling up the feedback form, your certificate will automatically generate and dispatched. Please fill up the feedback form. So you will get the certificate automatically. If you are choosing the checkbox for the requirement of the feedback form, certificate, you can just check it. You will get a certificate. Yes, so we have the Google group as well as the Telegram group, WhatsApp group. Become the member of all these things. Now we'll get a notification from our events of our programs frequently. And our next PSL program is going to be in University of Madras campus. It's going to happen on 8th of January. So there was an interesting treatment done for cancer. So they did the treatment through gene editing. It's going to be taught by Dr. Indumadi Mariappan from LV Prasad Institute, Hyderabad. And we also have one more cancer specialist, Dr. Priya, but Ramanathan from their Cancer Institute, both will talk about that. It's also going to involve chemistry. So those who are interested in chemistry, it's going to be a biochemistry, please come attend that one. It's going to be on Sunday, social is going to be on Sunday, 4 o'clock. So we will send the notification to all this. So let me wind up by saying that what are thanks? So anyone? What are thanks?
Please.
Come in here.
Thank you all. Names. Thank you for the experiment. In PSL, so far we did theoretical explanations. I think this is the first time we are conducting the experimental event. So I'm also very excited. Even though it's all a basic chemical reaction, mostly we done in the theoretical things as well. But currently we saw the both theory and practical things. So thank you for that, sir. Also, sir, thank you for that. So to organize this event, we are thanking Seminary Library Management. Thank you all. For next event, you will receive a notification soon. Please participate. Thank you all.
Thank you very much. So, exciting event we're going to have. So, PSL, although we have 6 declined, I would say that maybe 5 to 10 is going to be very exciting. The participants, participants are very much excited and they are part of the event. This is one such thing. Thank you very much, sir. We'll have more such thing in future. We will also organize Chitrai Fest in April for summer camp for the students. So that's going to be, we are planning it and we'll announce it. So definitely we'll include the chemistry as well. Thank you.
Excellent. Excellent.
How can we get the recording, sir? How can we get the recording, sir?
Sadam